Okay. You declare it on the Google group. Today that the class will be only from 11:45. Okay. So what we are doing is today will be a very difficult subject for chemistry background, but even in physics it is not. So we have tried to do interacting systems where molecules interact with each other, and we have done Mayer's theory, and Mayer's theory, which is gave rise to many other theories, but that is essentially theory of real gases and condensation. Something I forgot to tell is that this is also called, we did the reason of that it breaks down at high density, but it is more famous in physics. This subject is approached by chemists and physicists in a very different way. This is called high temperature expansion. The reason it is high temperature expansion, if you look at it, that the Mayer function A, which is e to the power minus beta ur minus 1. So when more temperature becomes large, beta becomes small, so F becomes small. So these kind of graphs that comes that becomes less important than these, and then these become less important than these. So at low density of gases, anyway this will be favored over this because there are not many molecules per unit volume, and these will be more favored than that. Probability will be larger, which will be picked up through the when you calculate the partition function, the cluster integrals and irreducible cluster integrals. But equally rigorous way of saying that the Mayer's theory essentially an high temperature expansion, and virial series is a series in density, but it can also be considered as high temperature because the higher virial coefficients rapidly decrease with temperature. So that's a different view which comes from e to the power beta u, and this high temperature expansion pervades all through statistical mechanics simply because of the Boltzmann factor e to the power minus the beta. So the difficulty comes in statistical mechanics because of the interaction between particles, and we cannot evaluate the partition function, we cannot evaluate the total number of microscopic states, and that's why these few cases we can do rigorously plays a very, very important role because they guide us and they provide us insight. Just like Mayer's theory went on to tell us what is a virial series and went on to develop many other things, like I told you, sol-gel transition, percolation, the clustering phenomena, the cooperativity, which is really, I explained, is a beautiful phenomena that you can have 10 intermediate size clusters, say in a particle of, you can have particle of 100, you can have 50 monomers and dimers, but other 50 particles can be distributed among the clusters which are 5 of say 10 particles. Now when you increase 1 or 2 more particles, these large particles can get connected because another particle can come in between. You can imagine it easily in a lattice, in a cell, that there are these clusters which are connected lattice sides, another big lattice sides, and then there's an empty between them. But as you increase the probability or the density, probability of finding a particle which is same as density, then that can get connected. So what happened in a very infinitesimal change, this 510 Mars can becomes 150 Mars. And suddenly these intermediate size clusters disappear from the system, and that's what happens. So in the rains, see, after rains, the clouds, all the things comes down, and sky become clear, and you don't see any humidity beyond the point goes down, and everything, at least upper atmosphere. So this is the same thing, the cooperative. So that in that sense, Bayes' theory is a great theory and gave a lot of things, but it also has its limitations. As I said, that it cannot be pushed beyond a point where everything diverges, and I cannot extend to low temperature and high density. But with that caveat, we'll go ahead and do the next thing. So second interacting system, which of great use in statistical mechanics and find great use in phase transition, and because it is solvable in certain limits, it can be solved exactly. It plays perhaps the most important system in the entire physics of interactive physics and chemistry of interacting systems, and this is the Ising model. Ising model is a simple one-dimensional Ising model. This is also same thing is there for 2 dimension or 3 dimension, but they are called 2 dimensional, 2D Ising, 3D Ising, but the original Ising is 1D. And then this is essentially you have a one-dimensional chain or rod, and you have the spins, which are spins, or you can take them dipoles, whatever, and they are interacting with each other. So they can be parallel, anti-parallel, all possible. So the spins can be, so definition of Ising model is that it consists of spins. Spins can take only 2 directions. So let me write down the assumptions of the model. One, spins can be only up and down. And they are denoted by +1 and -1, as if one is the +1 and minus comes to a great extent from the logic that you have an external magnetic field. So these are only for magnetic systems. You have an external, also it goes over for electrical systems. We use that in real dipoles. Okay, so now these spins can be up and down, and they are denoted by +1 and 1, and the variable that comes is sigma I, and sigma I can be +1 and -1. If it is +1 is up, and is -1 is down, and what I stopped telling in a minute ago, that why this is chosen, essentially because you have a field in mind, and cos theta, and so up is the field is aligned on the top. That's just a nomenclature. You can do it any direction you want, but up and down cannot change in Ising model. So it's cos theta and cos pi, so +1 and -1. That's the logic of these two things. Then number 3, an important, very, very important thing, that I have only nearest neighbor interaction. Only nearest neighbor interaction. That means this pin here can interact only with this one and that one. Okay. So in a finite spin, when we want to finite chain, we want to do in order to reduce the effect of the boundary, we impose what is called a periodic boundary condition. That means we form a ring. So after that, it becomes this one. This periodic boundary condition, which is used in many areas of these chemistry computer simulations. Okay. That not a part of the assumption. The part of the assumption are these three. The spins can be only up and down, and so you do by plus and minus one, and the only nearest neighbor interaction is taken into account. So given that, you would imagine that's a trivial thing to solve, but it turned out no. It's highly non-trivial. Nobody has been able to solve three-dimensional Ising model. There at one time there were sporadic claims of three-dimensional Ising model, but has not been able to do. Nobody, the previous people have tried. Nobody has been able to do. And the 2D Ising is exceedingly difficult, and still called the most difficult calculation in the history of physics. And that was done by Lars Onsager. So, a physical chemist. Very interesting. Now, so we go now, write down an Hamiltonian, what called Ising Hamiltonian. That you wrote down the H equal to. Okay, let me write down the A1, then general one. Okay, so I now spend some time on this. So this is a generalized version of Ising model, where the interaction depends on the location. That means this interaction can be different from this interaction. So if I call that 1, 2, 3, 4, 5, 6, then 1, 2 can be different from 2, 3, and this plays a very important role later, but we don't need it now. So we'll consider them to be constant and take it out. So J sigma is sigma J. Okay, so this done such that when these are both up or both down, then I get plus for both of them, and then it becomes minus, and that is favored, and that is called ferromagnetic interaction when parallel spins are favored. Similarly, -1, but however is a plus and minus, like in this case, or in this case you have 1 plus 1 minus, so that becomes -1, and this becomes plus, so that is not done. And now this is the magnetic field. So magnetic field, now if I again a matter of convention, these are all matter of convention, but they are perfectly general. You can change convention. If you don't like this convention, results will not change. So this is the magnetic field that is acting on it, which absorbs in it to combine the dipole moment or magnetic moment of the spin and the external electric field. That means a magnetic field is H, and then magnetic moment is mu, then B is H mu. So that is combined in that. The effect of the external field is important. Of course, you can have statistical mechanics in the absence of the external field also, which we'll do. But this is the major thing to know. This is the Ising Hamiltonian. This is a general Hamiltonian, valid for any dimension. You can have 2 dimension. You can again have spin up and down. Exactly same thing. In a square lattice, the number of nearest neighbor, here is 2, it becomes 4. If you go to triangular lattice, then number of nearest neighbor becomes 6. Then you can go to FCC or BCC lattices. and which are just an historical comment that when you go to 3 dimension, you cannot solve it um, analytically, and you do fall back on a high temperature expansion, which is very similar to Mayer's. It's really interesting. And huge number of people till the 60s and 70s used to do these high temperature expansions of the 3-dimensional Ising spin. Very, very famous scientist, Don Breed. Okay, so we have now defined the Ising Hamiltonian. And now I'll spend a little time telling you why such a simple Hamiltonian. It might not look so simple to you because if you are not used to kind of abstract things, so this is sum over I, and this is sum over given one configuration. This is, so I have 1, 2, 1, 3, 2, 3, 2, just like we did in Mayer's theory. Okay, so this Ising Hamiltonian, I'll now spend a little time before I go to calculations to tell you what are the basic merits and certain things of this. Actually, what I have in notes is much better than written, but it is better than that. But let's see, this will do a little bit of the work that I intend to do. There's too much data here. Okay. So these are lattice models. So some of them analytical solution is possible. Okay. So this is the spin that I am talking, a chain of n spins, and this is the Hamiltonian, the Ising Hamiltonian, and you can understand now what is important thing to realize that, and very important to realize, there are n spins. Now at any given instant or any given configuration, these spins are all having configuration which could be which is different from another configuration, but each configuration comes with an energy. So a given configuration, this Hamiltonian is for a given configuration. Okay. For example, let me consider this one. I will pick up a minus from here. Let's see, magnetic field is 0. I don't need it now. I would not need it for some time now. Now, I'll pick up a positive contribution from here, another positive, another, for some reason everything positive here, the person who do it is all antiferromagnetic kind of interaction. Okay. But if it were up, then as I said, so a given configuration comes with a given energy, which is exactly same we have in gas phase, that where at any given configuration, a number of particles are interacting with each other, and that configuration has an energy. And Boltzmann taught us that the weight of that configuration will be given by the energy of that configuration. And this is very essence of the statistical mechanics, how we build the thinking in statistical mechanics. Okay. So again, the Hamiltonian given, here one says what is ferromagnetic, what is antiferromagnetic, all these things. Okay. Now, how to do the partition function? Now in partition function, this Hamiltonian has to go in the numerator of the exponential, right? Minus this there in front of minus beta h. That minus takes care of the minus and minus here. I get positive. Now, the difference between the my earlier thing is that I have to add over all the configurations. So, before so the sum over spins goes here in the exponential. But this is weight of a given configuration. But I have to sum over all possible configurations. So this is the same as in my classical or continuum statistical mechanics, the integrations over positions is the same as the sum over spins. There I take a configuration, particles are in the position R1, R2, R3, R4, Rn, and then I get an Hamiltonian for that. Then what I do? I integrate over all possible positions of the first particle, second particle, third particle, dr1, dr2, drn, which is exactly same thing we are doing here. We are taking over all, summing over all possible spins. But now you understand that it creates enormous number of configurations. Because each spin, though only can be up and down, it has a, if n number of spins are there, they are 2 to the power n. And if n is large number, like Avogadro number, then you have a huge number of configurations there. So the entropic part enters through all possible combinations, and the Hamiltonian comes. Okay, so now the partition function is this thing. This we need not worry right now. Okay, so okay, now I want to there are going back. So the Ising models are explains properties of is particularly for Ising model, solids, polymers, micelles, reverse micelles. This simple thing is used rather extensively, and also the Ising model that we do is used for gas liquid transition, even condensation. You can have a Mayer's theory version of the Ising model, or Ising model version of the Mayer's theory, and this is the one was part of PhD thesis. Okay, now what I'm going to do, I'm not going to do this difficult thing. I'll do something little simpler, and because it could become very difficult, and so I think I have explained that this particular spin comes with an energy. That energy goes to Boltzmann factor in exponential, and that gives the contribution to partition function of this particular configuration. This is not good. I think that's the one we discarded, right? Yeah. Okay. Now I'm going to consider only this part. I'm neglecting for simplicity now, because I'll be able to do something. So this is now deleted. So I now have a partition function UN as a function of T, n number of spins at temperature T, sigma 1, sigma 2, sigma 3, sigma n, all the spins, then e to the power minus beta j sigma 1, sigma 2, sigma 2, sigma 3. So this is the partition function I need to evaluate with the condition that sigma 1, sigma 2 are, they can take up and down.
It should be plus. It should be plus beta.
Yeah, that should be plus. Thank you. So now, you notice the one thing, that all these are coming as product. So I can introduce a composite variable sigma j c equal to sigma j minus 1 sigma j. Now let me see what are these composite variables will take. Now composite variables will be when this is plus, then minus, again plus, it is a plus, minus. So composite variable, while each of them have two variables, composite variable has four variables. Okay. So this quantity now, I can now write in terms of composite variables, which is right. Now, I can now calculate this contribution of, okay, this of course I have to do when j greater than equal to 2, because I have 1, 2, 2, 3 like that. So j goes from 2. So in this case, j has to go from 2 to particle count. Okay. Now I have to do this composite variable. So now I write this as I bring the product outside and I take the sum inside. Sorry. This is my composite variable now. Sigma j c. Okay. Then e to the power beta j sigma j c. Alright. Now I can take each one j and let me calculate the composite variable. So now that will be e to the power beta j sigma composite variable c and sum over say j jet speed. Then sigma jc has 4 values. So that will be e to the power plus beta j plus minus e to the power minus beta j. I have plus minus e to the power minus plus both minus. Then I have plus minus and minus plus. So that would now be 2 into e to the power beta j. It is beginning to take the character of, you'll see later, Ising model. So this is what I have done actually is equivalent to a factorization. I have factorized. I could factorize because of this form of, what I deleted, the form of that thing. So I have done a factorization, just the factorization you do. But that factorization suddenly gave me a wonderful form which now does not depend on j. Just the beauty. Then what I can do now? I can make this product here. So now I can replace now this by so many times the product, we got n minus 1, but n is very large, so I don't really care of that. So I have evaluated the partition function in the absence of a field of the Ising model. Let me do some work with that now. The way I always did was like this. This is the way I always decompose, factorize. That's the way I learned. But in the book that we have written is not like that, and that's the lacuna we have to really correct, because this is the way one should go. But most of the books jump into, probably Carson Huang has this way of doing things, because I remember that this is in many places the composite variable. But I'm unfortunately most of the places I looked into, you start with a very complicated transfer matrix, all these things, which is at least for us for physical chemistry background people is not a best way to start these things. Okay, now there's some extremely important thing coming out from there. Now free energy A, okay, that is then I'm just neglecting n is very large, so I'm putting that equal to n. I hope I'm doing all this right. Now, what is this quantity? E to the power beta j plus e to the minus beta j? 2 cos. Okay. So now, again 2 to the power n. So then kbt, I have a there, so this term I want to write, take it out. So plus 2 in kbt ln2. Please check me if I am doing anything wrong. So these two cancels, right? These two cancels. So I'm left with partition function now. The free energy, sorry. So in the absence of a magnetic field, I have obtained the free energy. I am obtained the partition function and the free energy. Now there's something very important here. This continues to be in the presence of a magnetic field. The important part here is that there are certain functions in mathematics which are called entire functions. Exponential is an entire function. Cos is an entire function. And what is an entire function? That has infinite number of derivatives and is continuous all through. That function is called an entire function. So this cos is an entire function. So it cannot show any discontinuity. If it does not show any discontinuity, it cannot show any phase transition. And this is one of the primary result of the theory of phase transition is that you cannot have a phase transition in one dimension. So this is also called a beautiful theorem, Ascoff-Mervin theorem, but we don't need to go into Ascoff-Mervin theorem at all, at least not in this kind of or rather preliminary things that we are doing. But it is important to know that these cannot show any singularity. So it cannot describe phase transition. I can calculate entropy. I can get a dA dt of that and get the entropy, right? I can get the specific heat. And then I can calculate the fluctuation in energy, specific heat, and then I can find those two are the same. All these things one can do. And people have done, because this is the one model which has been beaten to death. But important result here is that because of this kind of beautiful expression, nice, neat, and analytical expression, that we do have a completely analytical function. So there was this gave rise to a lot of logic and lot of controversy, that a little bit of history, that how statistical mechanics can at all describe a phase transition. That means since Boltzmann is exponential and exponential is an entire function, differentiable completely to all order, how come then a statistical mechanics, which is in the form of the sum of the exponentials, as we have seen it here, sum of the exponentials can give rise to a singularity. That was a huge debate in for more than 2-3 decades, which was ultimately solved in a specific case by Onsager, but in a very general case, a beautiful by C.N. Young and T.D. Lee, called Young-Lee theory, Lee-Young theory. Two very famous physicists who also did quark and parity violation, and they went on to get the Nobel Prize for that. But their another beautiful work was showing how, and they used the Ising model and used the Mayer's theory, actually more Mayer's theory than Ising model, to show that how singularity can evolve by doing a beautiful piece of complex analysis that we can do sometime. Okay, so this is with the in the absence of a magnetic field. In the presence of a magnetic field is a little bit difficult, so I'll not do it in the class, but I'll go through that little bit, and then I'll give you the final result. It's not too important that we do it for the major course of the thing. Those of you who are interested, you can do it, and if you get stuck, you can come to me and I'll do it. Okay, so now the way it is done is to recognize, you can go over that you recognize that you can decompose the partition function just like we did. You can decompose the partition function in terms of a matrices, and these matrices are very simple matrix. These are the matrices that it comes. So these are the diagonal terms, and you can essentially use this matrix to propagate the nearest neighbor correlations to all order, and you do very similar thing that you have done here to the power n. And then, but you cannot decompose completely like that I have done here, because of the B introduce an asymmetry in the problem. The symmetry that I have in this problem, that is broken because of this term, because here now here 2 down comes with the same term with 2 up, but here that is reflected here, 2 up and 2 down are not the same, because see B is the magnetic field. So when you are going down, then magnetic field, if the spin is up, then both the 2 spins down will be unfavorable, so that will come as a plus sign. The otherwise both will be both spins up, that will come with a negative sign. So this symmetry of this Ising Hamiltonian in the absence of the magnetic field is broken as it should in this case, in the presence of the magnetic field by this term. Then one can solve this. Let me tell you by transfer matrix method with the diagonalization. The reason of my not doing it, it uses some theorems of eigenvalue analysis, which will take a long time to do. That I am not going to do, but I'll tell you and there is some examples done. You will see that particularly what happened when you have these kind of spins, which are kind of things that I have a little better than how one configurations gets energy, and how you can calculate the eigenvalues of such things. But let me tell you the result. Okay, and the result is interesting, but not almost the same kind of thing that we have. So this is the partition function now. That's what I was saying. It includes the calculation of the eigenvalues, which you find most of the books assume the eigenvalues of this matrix. This matrix, you have to find the eigenvalues of that matrix, and then you notice that one eigenvalue is larger than the other eigenvalue, and then you can like here these 2 eigenvalues analysis done here, and one is larger than the other one, so in the end going to infinity, one of them remains. But let me tell you the basic result. The final result is this: the partition function IQI for Ising in the presence of the magnetic field is a considerably more complicated, but still analytically doable. You can go through this. These have to be done analysis. Then you have to do certain. It's not too difficult. Very similar thing that we did in the absence of the magnetic field. Same factorization, and then the sum over all these things. This is the theorem I was saying. I am not comfortable about doing that. That quantity is the trace of m to the power n. And then of course you have to have certain kind of unitary. This is a symmetric matrix. Then unitary transformation of the symmetric matrix, and then partition function come as this diagonal matrix, diagonal to the power n, and then that is this to the power n. This is then the diagonal matrix to the power n is exactly equal to that. So I don't want to go through all this, but these are mathematics you can do, and they are not difficult mathematics, but you know you have to do them. All right. So this is the this is all given there. So the partition function then becomes this thing at one. And look at that, how much more complication we have when the electric field, magnetic field is there, and then you go to, if I would be equal to 0, then it will go over to the old form. Then we can calculate the free energy, cavity Ln Q Ising, using that Ising, and then you can get the, as I said, one of the eigenvalues survive because other ones is more. So n going to infinity limit, this is negligible with respect to that one. These are the asymptotic analysis. And then you get this free energy. And this is very interesting. Once you have free energy, then we can do some work with that. We couldn't do something over there in the earlier one that I have worked out here because we didn't have magnetic field. I could have do entropy and I could have done specific heat, but I couldn't do the most important thing that people want, which is the magnetization. But if I have the free energy, I can do the magnetization. Now, can you tell me how to get the magnetization from this free energy? You know, I know I'm dumping some equations on you, but they're not really very difficult. Beyond what I've done here was the tricky little thing. After that, it is same. Though you have to do the unitary matrix transformation, you have to do the eigenvalue analysis, all these things. It will take more than 40 minutes to do. So I'm just avoiding doing it. How do I get, when I have the free energy, how do I get the magnetization? Lighter? Right? Yeah. So all I have to do di dB, and I get the magnetization. Okay, that is done here. Then magnetization is with respect to magnetic field, and H is same as B, magnetic moment taken out. Okay. So this is then this quantity. Then one can calculate, going back to same as this lambda plus and all these things, and okay, and then you get, call that or combine this as Y, and then we have taken with respect to magnetic field, and that's why you have to take care of the magnetic moment. Will come here and there, change of variable, I have to absorb it here because this is the quantity that I need as my magnetization. I want to go back the variable I have in my work, which is this Y, and Y is this quantity, beta B, and then I can take the derivative. These are the ugly things that one doesn't want to do in the class, but you can do it. Fortunately, it is done here. So I can do the derivative of this ln. So this guy comes in the denominator, and you take the derivative, you get two terms. Okay. Taking derivative of cos and all these things is certainly not the most pleasant thing in the world. So because there are two terms there, but you can do it. But essentially, I think everything is clear here, right?
Nothing should be complicated. Doing the board is complicated, especially science. I'm mortally afraid of science. Okay. Now we get this beautiful expression. However, at the end of the day, you can simplify that. That remains, this remains, and there is this gets simplified, and I think we have to redefine variables as x, not x, maybe p and q, small p and small q, and again do that, and this should become the same as this. I think we have to think of, we have to go back to e to the power x and e to the power minus x, or e to the power y and e to the power minus y, and square all this thing. Then we have to combine term. I think here also you have to combine term. This and this is the same, and that is different from this one. But whatever. This and this is the same. So I think there is certain manipulation one needs to do that. I have not done that for a very long time, but you can do that. But at the end of the day, you get the magnetic moment, which is experimental observable quite easily in these magnetic systems. You get a completely analytical form. That is the main thing. That is a sinh, and sinh is as analytic as cosh, hyperbolic cosh. So, and now I plot that against 1 over temperature. Now, if there were a phase transition, what would I expect? I'm plotting is 1 over temperature. So, this is the high temperature limit, and this is the low temperature limit, right? If there is a magnetic transition, paramagnetic to ferromagnetic transition, then what will happen? Now tell me, what is the ferromagnetic state? Tell me, what is the ferromagnetic state? See, one of the reasons that physics course, they learn it very quickly, very rigorously in your first year. You learned it, but not in terms of spins in your schools. They should have taught you in terms of spins. They need not solve the Ising model, but they should have told you about the Ising model. But that's not done, not in Indian context. But Ising is a very beautiful thing. And the little thing I did, the little thing that I did here could have been done in high school also. But doesn't matter what the solution. Forget about that, what has not been done, not done. Now tell me, what is the ferromagnetic state? See, we are doing phase transition, and now the most important phase transition is the magnetic transition. Then metal insulator transition, which is huge amount of industry runs on that, right? Then semiconductor superconductivity. Did anybody teach you magnetism? Huh? Magnetism has not been taught at all. But in the integrated PhD, it has not been taught yet. They should have taught one magnetism course. Electrostatics, electromagnetism, because we had that a little bit in our honors course. We had it one small 16, half of a course in Calcutta University, magnetism, and then I took a lot of courses there from physics department. But I tell you that it's really rewarding. Those of you going to material science and physical chemistry, I hope some of you are going there, because that's the most fascinating area now. And let me tell you, organic chemistry is not that fascinating anymore. It's going on and on and on, the same kind of synthesis. Well, you can get some job, but it's very boring. So most exciting things are happening at the world of material science and world of biology. Materials is particularly exciting now, as you can see. Your TV getting changed, your mobile getting changed, every technology is getting changed in every 2-3 years. Huge amount of work going on in all these companies, IBM, Samsung. We should do more of this. Now the artificial intelligence is going integrated with okay. Ferromagnetic is that when all these spins are parallel to each other. That's the ferromagnetic state. And paramagnetic state is that when the spins are random. So ferromagnetic state is the state we call ordered state. and parameter is the disorder state. So what you are talking of, an order disorder transition. It's very important thing. Please write it down. Order disorder transition is an example of order disorder transition, which is same in melting, which is same when you have a beta brass, which I believe is zinc and copper, right? And that undergoes a fabulous transition, which is a huge change of material properties. So, and we use that material properties many times. You see, when you use the valve, safety valve, that we put an alloy, and a little change of temperature change the properties of the alloy. That is the basic of this, many of the valve in these complex systems. So these are important thing to know, because chemists make these things, and then we just give it to for physicists to do everything, characterization. If we understand, we could have make much better material probably. Okay, so the order disorder transition. Then what would happen in a real system? You'd see that there would be a hysteresis. There would be sudden jump of magnetization. This is 1 over temperature, so it will be other way around. If I put temperature, it will be like that. Otherwise, it will be like that. Go like that. So that's a and these systems show the hysteresis. And as I told you, a system that shows hysteresis is the first order phase transitions. However, the beauty you see in a two-dimensional system, that even in the absence of the magnetic field, there is a order disorder transition where the specific heat compress magnetic susceptibility, so that diverges, and that's the characteristics of an order disorder or a critical phenomena. So the one of the things that Ising model can use us, and that I am going to use to take you to a critical phenomena. Okay, so before we go, so this is the, as far one-dimensional Ising model goes, I have derived a part of it, the basic thing, and I have, it is given here. We'll put it in the A. If we want to make a little changes, I'll probably make a little changes on this chapter and send it to you. But you can see there's a unitary transformation going over to diagonal, then to the power n is lambda 1 lambda n, and here you have to work it out, find out the eigenvalues. And here the same thing I have done, exactly same thing does here, that you go to a factorization. The same factorization comes here. That allows me to write it into n. Same thing m to the n I wrote here. Okay. But then you have to go by eigenvalue analysis. I could sum it up here because I did have this symmetry, which is not here. Okay. So now this is a hugely important thing, an extremely difficult thing at the same time, the two-dimensional Ising model. I will just tell you the result now, and I'll do something else, which I want to teach you something else, which is the other part of Ising model, many other techniques which are very useful. So but let me continue a little bit with two-dimensional Ising model. I'll come back to the two-dimensional Ising model. In a normal course of event, I would not have two-dimensional Ising model at this stage. I will have a little later, and that's the way I teach. So two-dimensional Ising model, when I have a square lattice and I put these pins, the beauty of this is that this model exhibits a phase transition, and this played a very important role. As I told you, in the whole history of almost history of science, that can be solved exactly, and that is it was done by the evolution of the partition function is extremely highly non-trivial. The feat was achieved by Unsagat, still considered the most brutal and difficult calculation done in the entire physics. And that has a very complicated free energy functional, which we are not going to. But most important thing, that has this magnetization transition. This is the model shows, and this is what you see in experiment. And it has, this fall has certain exponent, which is called critical exponent, and that is the things, critical phenomena, that we do a little later, study of the critical. Now I want to do not the solution, this is a highly non-trivial solution, but I want to do, this is what I want to do now, and I want to start is there are certain ways. Okay, there is a very important thing in magnetization, which is the Curie point. Now, can you tell me what is the Curie point? I really strongly recommend that you guys, I'll send you some material, but you read up the magnetism. It is really not fair not to know about magnetism. That is not fair. Even if you are doing, I at least indicate PhD students are after all doing PhD, right? And you would need, even you are doing organic chemistry, the magnetic properties you have to study. And many of the things, the magnetic properties of organic materials, organic, that you know why magnetic is so important, magnetic properties are studied. The reason is that sometimes you have a lone pair or some characterization you need. So you need to know the basics of magnetism. Okay. So these are the, we'll make a beginning. So the way I'll go now, let me write down and I'll come back and forth. Few things you should certainly do. Go through the derivation. This will take you time, about an hour. Or maybe a little bit more, but this is worth doing. So the flow that that I'm going to do is, we have done one-dimensional Ising model. We will not do, and we done the magnetization and everything, and show there is no phase transition. No phase transition. There was a little bit hint of that, why it's the phase transition, that will come back later. Essentially because the new phase cannot be stabilized with only two nearest neighbor. And next what we will do is they called mean field theories. There's a huge list here. In this context of lattice is Bragg-Williams. Then the same as van der Waals, a much simpler and more elegant way is Landau. Landau theory, we did not do Landau theory yet, right? Oh, so we'll do the Landau theory after we finish these things. So in the mean field theories is, you have done one example of mean field theory, that's what I was asking, Curie temperature of the molecular field. What is the Curie temperature? And also called Curie-Weiss theory or equation. What is that? Magnetization equal to 1 minus T by Tc. Remember that? The magnetization goes to 0. But magnetization goes to 0 with the exponent 1. If I go T minus Tc, then T minus T minus 1. And that is not correct. People found that we saw the 2D Ising is a very different experiment. Okay. So the Curie theory, the way it was developed, we'll see that, was a mean field theory. Mean field theory is the following concept, that we have is a very important concept, but fortunately they are understandable in a very simple physical way, and that's what we'll do. And you will like the Bragg-Williams. I'm not bragging, but I once had the good fortune to teach at Harvard a really formal course, a course like that, StatMech. And there's a great hall called Pfizer Hall, where many great people have presented their results, and the, next to it was great Bob Woodward's laboratory. When you are that legend, Lipscomb and all the legends are there. But when you teach at that hall, the beauty of that is that when I go to teach, I used to teach from 11 to 12, 3 times a week. Everything is pakka. That means there are nine one screen, and screen can be taken out, and 9 boards. 9 board in the following sense: 3 row and 3 row 3 column, and you press, you start from one side, do this, do that, then 3 goes up, you press, and then 1. But more important, that's not. But what I'm saying, when you enter, the secretary, I told them, secretaries, in the morning I want my coffee for me and my students when they are rich. So there is a coffee there, and everything was clean, all the chalks were ready. You know, that's what the secretaries are supposed to do. Here, God knows what the secretaries do. Most of the time, they don't do anything. And we are not assigned job to them. So coming back, so this, now I've got something nice. I complain a lot, but that's, things improve by complaining only. Okay, so the mean field theory means I have, so let's say nearest neighbor. So I have spins here, spins here, spins here, spins here, and these are first nearest neighbor, right? And second nearest neighbor are these 4. Okay. Now all the everywhere there is a spin and spins. So what is the main effect of the other spins on my central spin? Think a little, because this will be continue with the next class. So let us consider a very high dimensional solid, higher than 3 dimension. You can stop at 3, but in your mind you can consider. Then number of nearest neighbor increasing. Okay, here I have 4. 3D in simple cubic will be 6, like that. Now, I can have a magnetic field or not have a magnetic field. These spins are, what are they doing on this? They are interacting. How they are interacting? They are interacting their moments. Now for a moment, if I say I freeze this one, then I'll add the effects of all these things. What my spin will see then? My spin will see an average effect. So that is, average and mean is the same, right? So then I'll have my spin here is seeing a mean field. So if all of them are up, then my spin here will also want to be half. So now can I take a description, little bit coarse grain, means opaque description, little bit, make it little, not completely microscopic, little bit less, we call it coarse graining, where I would be able to talk of the, I write the Hamiltonian now in terms of the mean field. Now what I do, these guys also acting on that guy, I can construct another mean field, and I can make them self-consistent. Okay, that is one probably layer upper theory. So this is the way one can get beautiful solutions. They show the phase transitions. We don't have to do as much work, and I told you anyway, 3-dimensional Ising model, we cannot solve anything. Nobody in the world has been able to solve. But you will see this is just like Van der Waals equation. So we'll do these beautiful mean field theories. They are the very favorite of people because this is much easier to do the calculations and much easier to apply. Otherwise, you have to do numerically in 3 dimension. And these mean field theories, as I said, very favorite of us, and we will continue with that in the next class. We'll finish mean field theory, and from the mean field theory, I want to go to critical phenomena. With that, we'll finish the formal aspects of phase transition, and then we'll go to phenomenological phase transition, another beautiful theory, almost with critical phenomena, Landau theory of phase transition that tells you how to think about it. And from the Landau theory, we'll go over to do the one thing which is very important in physical chemistry is nucleation, which is materials, extremely important. Not taught in physics department, but nucleation and spinodal composition, and these things are far more important to chemistry. Okay. Thank you. I'm under a lot of pressure these days because there are a lot of things going on. Huh?